Welcome to lesson 1.09. Two different aims, but both in the same vein. Make sure you copy both down. We're going to be solving linear and quadratic systems of equations, both algebraically and graphically. And we're going to recognize when a linear and a quadratic system have no real solutions and justify that answer both algebraically and graphically as well. Okay, to get started, here is a couple of questions, 3 questions to be precise, that are going to allow you to sort of discover and think about the methods both graphically and algebraically for solving a system of linear and quadratic equations. So go ahead and write these down, give these a shot on your own, and we'll talk about them briefly, and these will lead into what it is that we're going to be doing with linear and quadratic functions. Okay, so the first question says, if you're given a quadratic function and you set it equal to 0 and then solve, what do the solutions tell you? And so graphically what this is telling us is, if we're looking at our xy axis, the solutions are the values, the x values, for which my quadratic function intersects the x-axis, right? So, if I were to get solutions like 5 and -1, then I know that that's where my quadratic function intersects the x-axis. In particular, that's where it intersects the line y equals 0, right? The x-axis is really the line y equals 0, okay? And so another way of thinking of this is just when we set our quadratic equal to 0 and solve, we're finding all the different x values where it intersects that line where y is equal to 0. Okay, secondly, if you set the same quadratic function equal to 5 and then solve, what would those solutions tell you? Well, just like we were told by setting it equal to 0, where the quadratic function intersects the line y equals 0, now we would know where the function intersects the line y equals 5. Right? Where is this function intersecting the line y equals 5? Okay, so we're starting to build a really intuitive and graphical understanding of what happens, what it is that those solutions really mean when we set a particular function equal to something else and solve. So now, what if you had a linear function, 2x plus 1, and a quadratic function, x squared plus 1? If you set f of x equal to the linear function, what would those solutions tell you? Well, hopefully you tried this on your own, and just to give you a basic idea, imagine that you have the function 2x plus 1. That's just some straight line. It might look like this. And if you set your quadratic equal to this line here, just like when we set it equal to the line y equals 5 and we set it equal to the line y equals 0, we were finding all the different spots, the different points, where our quadratic intersects this linear function. And what we're really doing is solving a system of equations where we have one linear and one quadratic equation, and we're finding the solutions. And the solutions really just are the points of intersection. Okay, so let's actually go ahead and go through with this example. So find the solutions to the system of equations below, graph both functions to confirm your solutions. So first we want to start with our understanding framework. So understand, we want to have a plan, we want to solve, and then we want to check. And so just understanding here, find the solutions to the system of equations below. So when I hear the word solutions, there are a couple things that come to mind, and the first is point of intersection. I'm finding the points or point of intersection between the two functions. Okay? And the second thing that comes to mind is a solution is going to be something that is true for both equations. So when I plug in that x value, it's going to give me the same y value for both equations. So I have that in my mind, and now I've got to think of what's my plan going to be for actually finding this. Well, just like I did when I wanted to find where a particular function was equal to 0, like when I was finding the roots of a quadratic, I can do the same thing here, right? I have this quadratic function, and I can set it equal to this linear function. And what that's going to tell me when I solve is it's going to tell me where the quadratic function and the linear function have the same value, where they intersect. So that's the first thing that I want to do. Okay, so notice here that I'm writing out my steps here, and this is really my plan combined with my work. So this is a great opportunity for you to make sure that you have a strong example and a criteria for success for what it is that you'd need to accomplish when solving a system of linear equations. So the first thing I'm going to do is I'm going to set the two equal to each other, and this is my most important step because it gives me a solid foundation for everything that goes forward. If I don't do this correctly, nothing that I find will be of any help. So I set the two equal to each other, and at this point I want to notice, right, I have a quadratic function on one side. And anytime I have a quadratic involved in an equation and I'm looking to solve, there's something that we want to use, right? That's the quadratic formula. Because if we try doing inverse operations here, what we're going to end up is going through that long process that we saw the very first day of class, which was no fun. And so we want to take advantage of what we did that day, and in order to do that, in order to use the quadratic formula to solve an equation involving a quadratic term, we need it to be set equal to 0. So what we need to do is manipulate this equation so that we have the quadratic, we have everything on one side, and then on the other side we have equal to 0, set equal to 0. So that's going to be my second step. Now, figuring out how to do this shouldn't be too tricky, right? I have the quadratic already on the left-hand side, and so I just need to move everything else from the right away from the right. So I need to subtract 2x from both sides and subtract 1 from both sides. And so now on the left, I'm going to have x squared minus 2x, and the 1's will have canceled, and so that will be set equal to 0. Now, I can go ahead and use my quadratic formula to solve this. I can also factor, so I encourage you to do either one, but we're going to go through the quadratic formula because that will work regardless of whether I can factor or not. Okay, so I've gone through and solved here. Notice that my c value is 0, and so that makes everything very, very easy. My b value is -2, and so the important thing to note is that I've set x equal. I'm solving for x. The quadratic formula allows me to solve this equation, and I'm solving it for x. So I'm telling myself, look, I'm solving and finding the x value, which will make this equation, these equations, true. And so I have 2 plus or minus the square root of 4 over 2, and square root of 4, of course, is 2. I can go ahead and make that addition here. So I have 2 plus 2, which is 4 divided by 2, and that gives me 2. So one of my solutions is x equals 2. 2 minus 2 is 0. 0 divided by 2 is 0. So my two solutions are x equals 0 and x equals 2. Okay? So those are the x values for which my two functions will intersect, where my quadratic and my linear function, my straight line, will intersect. Now, I can go ahead and I can find the actual points where these are by plugging 0 in for my x value into either one of these equations. Remember, because either one is going to give me the same y value back out. So I could think about the point 0. Well, when I plug 0 in to this linear, I have 2 times 0, which is 0, plus 1. So that point there corresponds to the point 0, comma 1. That's one of the points of intersection. And 2, well, if I plug 2 in, I can plug it in this function here. 2 squared is 4, plus 1 is 5. So notice here, 2 times 2 is 4, plus 1 is 5. So the other point is going to be 2, comma 5. So what I can say is these two functions will intersect at the point 0, comma 1 and the point 2, comma 5. Or I can say that the solutions are the x values at which the two functions will intersect, and those are when x equals 0 and when x equals 2. So make sure that you have that written down, your final written out answer, and I'm purposely not going to write that down so that you can go back and put that in your own words. Now what we want to do is graph both functions to confirm our solutions. So to go ahead and sketch a graph out, now we know kind of where those are going to be. what I encourage you to do is use a calculator or Wolfram Alpha. And if you go to Wolfram Alpha and you say graph and then type in each of these separated by a comma, it will graph both of them out for you, or you can graph it on your calculator. So let's take a look at what that should look like. Alright, here we have it. So notice the blue function is x squared plus 1, that's my quadratic, and the red function is 2x plus 1. And notice here that the 2 points at which they intersect are exactly what I found. First point, 0, 1, and the second point, 2, 5. Okay. Alright, let's go ahead and make sure we have some of the key terms that we talked about written down, and then also discuss a couple of other possibilities for types of solutions we could find. Alright, so a system of equations, these are some definitions that you want to write down. It's just a collection of two or more equations that have the same variables. So if you had two equations where you had different variables, it wouldn't make sense. You wouldn't really be able to solve them. But if they have the same variables, for example, x and y, you'll be able to solve them. The solutions to a system of equations are the point or points of intersection where the equations have the same input and output values. So as we saw previously, those solutions are where the two functions will intersect. Now, what I want you to think about is the possibilities. How many solutions could we have to a system of equations where we have a quadratic and a linear? We saw an example of where we had two different solutions, right? And remember when we talked about how many solutions an equation involving a quadratic function will have? Remember, it's always going to have two. But what could those two be, right? We could have two distinct, remember this is for a quadratic and a linear, two distinct real solutions. We could also have one repeated real solution. And we could also have two distinct complex solutions. So just think about this for a second. If you were to have a system of a linear and a quadratic, two functions, one straight line and one quadratic parabola, and you set them equal to each other, you went through the process we just described, and you found that in solving your quadratic formula that you got two complex solutions. What would that mean about where your two functions intersect? Well, I'm sure you guessed it. They wouldn't intersect on our xy plane, right? Because these two complex solutions, they don't exist on the xy plane. So when you're going through and solving, if you find that you get two distinct real solutions, that's great. It'll intersect twice. If you find that you get one repeated real solution, then it's only going to intersect in one place. You still have two solutions, they're just repeated and they're the same. But if you find that you get two distinct complex solutions, that means there are no places where the two functions are going to intersect. And of course, you can use the discriminant to determine which of the three possibilities you're going to have. Alright, so I'm going to go ahead and give you an example now to try on your own. Make sure that you go all the way through with it and check your solutions graphically. You can graph it by hand if you want, or go online and then sketch the graph out yourself. Alright, so this problem has a couple of different parts. First, you're going to solve the following system of equations. Y equals x squared plus 4, and y equals negative 3x plus 7. And then you're going to give an example of a system that has no real solutions. In other words, you're going to write out both of the functions, g of x and f of x, one being linear, one being quadratic, where they're going to have no real solutions when you solve them. And then 3, explain why the system has no real solutions and sketch a graph to corroborate your explanation. So make sure you go through and answer all three of these. If you need a little kind of help in understanding where to start, go back, take a look at our example, go through the notes again, but make sure that you are answering all three of these